Good morning. My name is Ardalan Kangarlou. I'm a researcher at NetApp's Advanced Technology Group, and I'll be presenting Chronicle, a framework for capturing and analyzing NFS workloads at line rate. This is joint work with my colleagues Sandip, Shete, and Strunk. The main motivation behind creating Chronicle was to gather insights from customer workloads and understand how our products are used in the field. These insights are gathered via trace capture and real-time analysis of NFS traffic. The insights facilitated by Chronicle can help in a number of areas. They can help with design and tests of new software releases and hardware platforms. They can also help with diagnosing problems and misconfigurations in the field. Finally, they can help the sales force with selecting the right storage platform for a given workload and for creating custom-made solutions for customers. Let's take a look at a few of these use cases in more detail. It shouldn't be a surprise to this audience that an IO by IO view of workload provides much richer insights compared to aggregate statistics, summary counters, and sampling methods. A few specific areas where an IO by IO view of workload are preferred are the design and evaluation of data caching, data prefetching, and data tiering techniques. Another example is the creation of representative benchmarks, where the benchmark reflects the actual distribution of ops into arrival times and the data dedupe rate in a workload. Another application of workload analysis in sales, workload sizing, which is a practice of selecting the right platform for a given workload, has been a big headache for many salespeople. Unfortunately, in many circles, workload sizing has become more of an art than a science. Even attempts to make the process more scientific, such as by asking customers questions about their IO rate, the number of clients, random reworking set sizes, are not successful, because oftentimes the customers don't know the answer to these questions. If there is a methodical way to get the answers to these questions, that would eliminate a lot of guesswork on the part of salespeople and would get customers products that better match their needs. So with these use cases in mind, we decided to create a framework for capturing and real-time analysis of NFS v3 workloads. We chose NFS v3 because that was the protocol most widely used by our customers. Because our goal was to characterize customer workloads, it was important that our tracing and analysis activities do not interfere with the day-to-day operations of customers in the forms of downtimes or performance degradations. So instead of instrumenting NFS servers or clients, we decided to go for a middle box design that passively monitors network traffic using port mirroring or network taps. We also wanted to support rates at the rates above 10 gigabits per second, because 10 gig Ethernet has become pretty standard in enterprise storage. And we wanted to run Chronicle on the orders of days to weeks, so we can capture daily and weekly cycles in a workload. We decided to use commodity hardware because that offered the greatest flexibility at the lowest price. While operating at line rate was important, we did not want to create a solution that could do only one function. Instead, we wanted to create an extensible framework that could capture other protocols and other application scenarios beyond what we demonstrate in this paper. So before I talk about the inner workings of Chronicle, let's review the nature of NFS traffic and the previous state of the art. Because Chronicle operates as a network middle box, it needs to process a stream of Ethernet frames. What is important is that NFS operations are encapsulated in RPC protocol data units, and they're both part of what is considered the application layer. Because TCP/IP layer is completely oblivious to the nature of application layer data it transports, it is possible to have PDUs that start in the middle of a packet, or to have a packet that contains multiple PDUs. Therefore, for us to reconstruct storage level semantics, we need to perform deep packet inspection, which is the process of looking at packet payload beyond network header. We also need to do TCP reassembly, which is the process of piecing together application layer data to reconstruct PDUs that span across multiple packets. So there have been quite a few works in the past in the area of NAS tracing. Anderson, in his FAST 2009 paper, proposed driver dump, which was the fastest software-only solution operating at 1.4 gigabits per second. Driver dump worked by modifying network drivers to storing packets directly in the PCAP format. Because these works were done years ago with less powerful hardware, it would be unfair to compare Chronicle with them solely based on performance. Instead here, I would like to highlight their other limitations. First, capturing packets through the PCAP interface is very lossy. Anybody who has experience with TCP dump and Wireshark knows that these tools cannot even sustain 1 gigabits per second capture, full packet capture. Even assuming we can get a lossless network feed, storing packets in the PCAP format requires a lot of storage bandwidth and storage capacity. For example, trace capture at 10 gigabits per second for a week requires about 750 terabytes of storage. So instead of storing raw packets, which is the PCAP format, we decided to perform deep packet inspection to identify fields of interest in packets. For us, fields of interest are pretty much all of the NFS and RPC fields and a subset of network header fields. Because we do DPI, we can also know where the read and write data occur in the stream of packets that we process. Therefore, instead of storing read and write data for data dedupe analysis, we store 64-bit checksums that are calculated at 512-byte offsets, which results in a lot of saving. Finally, we leverage data series, which is a very efficient trace format for storing structured serial data. Also, by leveraging data series, we get inline compression, non-blocking I/O, and delta encoding. However, none of these come for free. They come at the expense of increased CPU utilization, which we somehow have to accommodate. Each data series file consists of a number of extents. Each extent type can be thought of as a table in a database. So we have extents for storing RPC, NFS, and network level information. With above techniques, a single standard disk can handle the storage bandwidth requirements for tracing at line rate. Now that we know Chronicle does a lot of processing in line, it is important to see how it efficiently uses resources. Efficient packet processing has been an active area of research in software routing and in network security. Some of the common techniques that are proposed in the literature are partitioning and pipelining work across cores for balancing work, judicious placement and scheduling of threads for maximizing cache hit rate, batch processing for minimizing context switching overhead. So here are a few examples that have been discussed in the literature. RouteBricks is a system that does packet forwarding at the rate of 10 gigabits per second. But performing more complex and CPU-intensive operations like routing and IPsec drops the throughput considerably. These authors admit in a follow-up paper that achieving this level of performance required tedious manual tuning. NetSlices is a user space solution that can route packets at the rate of about 10 gigabits per second by imposing fixed mappings between packets and cores. Recently, we have seen frameworks like NetMap and DPDK that work by modifying device drivers that bypass kernel altogether. These frameworks can operate at the rate of 10 gigabits per second, but creating more CPU-intensive solutions again drops throughput considerably. So it shouldn't be too hard to see some of the limitations of this previous work. They all have a network-centric view of packet processing, which entails just parsing the network header. They do not do any DPI, any TCP reassembly, or stateful parsing across packets. As a result, they have a fixed small per packet processing cost, which justifies the use of one core for processing packet. Another problem is that many of these tools, they require intimate knowledge of the hardware platform as far as number of cores and their topology. One of the big downsides of most of these frameworks is that they impose management of shared resources and state on the application programmers. So the burden is on the application programmer to use locks, thread-safe queues whenever necessary. So the main challenge for us was to extend these proven techniques at the network layer to the application layer for a more CPU-intensive use case and in a programmer-friendly manner. So let's see how Chronicle does packet processing. At the heart of Chronicle lies a user space actor model library called libtest. We wrote libtest for a few reasons. Libtest helps us as far as performance with seamless scalability to many cores. It also does implicit batching, which helps with achieving high throughput. As far as flexibility and usability, libtest enables a pluggable pipeline architecture, where by plugging the right modules, we can do trace capture, real-time analysis, or both. Because libtest hides the underlying hardware configurations from users of libtask, the resulting software that is very portable. Also because of libtask active programming model, application programmers don't have to worry about many concurrency bugs. We also decided to leverage NetApp instead of libpcap for reading packets for the reasons I mentioned earlier. The only change we made to NetApp was to be extended support for jumbo frames. So for those of you who are not familiar with active programming model, here's a quick overview. There are two main concepts in actor model programming. An actor, which is a computation agent that processes tasks. And message, which is the information to be shared with an actor and determines what actions the actor needs to take. One important aspect of active programming model is that there is no shared state. So that means actors cannot, for example, share variables. And because of that, we can avoid many concurrency bugs. The only way actors can affect each other is by sending messages to each other to a well-defined API. Upon receiving a message, the actor may do some computation, it may create a new actor, or it may send a message to other actors. Or it may terminate an actor. So with this overview, we decided to write our own lightweight actor model library in C++ instead of leveraging languages such as Erlang and Go for better performance and for finer level of control. Later in the evaluation, we will see how libtask fares against these languages. There are three main constructs in libtask: a scheduler, a process, and a message. So we already covered the last two in the last slide. A process basically is the same thing as an actor, and its implementation can be thought of as an event-driven state machine. A scheduler is the entity that is responsible for running processes. Each scheduler has a queue of processes, and it runs them one by one. Typically, we have one scheduler per logical core on the system. Similarly, each process has a queue of messages, and running a process entails processing these messages. Now let's see how libtask does load balancing and enables seamless scalability. When a scheduler runs out of runnable processes, it starts stealing processes from other schedulers in the system. Seamless scalability is also achieved the same way. So if we go from a 2-core system to a 4-core system, this type of process stealing results in the software to scale to more cores. We have implemented 2 versions of libtask. In the NUMO-aware version, the schedulers are pinned to specific cores, and they prefer to steal processes from schedulers that are on the same NUMO node or on the same CPU to preserve cache locality. In the NUMO-agnostic version, schedulers are not pinned to cores, and they have no preference in stealing processes. So we have implemented Chronicle as a collection of libtask processes and pipelines of libtask processes. Each libtask process corresponds to a module in our architecture. So we have a module for reading packets, a module for parsing network header, and delegating further processing across one of our pipelines. Here are 2 examples of Chronicle pipelines. The top pipeline is used for capturing traces. Here we have modules for parsing RPC header, NFS fields, calculating checksums of read and write data, and for storing traces in the data series format. The second pipeline is an example of real-time analysis that Chronicle can do. This pipeline basically computes in real time the parameters that are used for workload sizing. As you can see, this pluggable pipeline architecture enables parsing beyond NFS v3 protocol and also beyond application scenarios that we discussed in the paper. The key module in our architecture is RPC parser, which does filtering of TCP and RPC traffic, reassembly of TCP segments, and detection and parsing of RPC header, among a few other things. RPC parser has two modes of operation. In the fast mode, finding RPC PDUs is pretty straightforward because the length of a PDU is part of the RPC header. So by advancing so much in the byte stream, we can find the next PDU. However, this approach fails whenever we have out-of-order delivery of packets or when we have packet loss. In this scenario, RPC parser operates in the slow mode, which means RPC parser has to scan every single byte in the packet until it can detect the signature for RPC header. As you can imagine, this process can be quite CPU intensive and slow. So I encourage you to refer to our paper for the functions of other modules in the pipeline for Chronicle's novel zero-copy application layer parsing approach, which obviously need to copy application layer data into a contiguous buffer to reconstruct PDUs, and for some of the insights that Chronicle facilitated and help our customers. To evaluate Chronicle, and to do our customer deployments, we use a commodity server. It's a beefy server. It has 2 CPUs. Each CPU has 8 physical cores or 16 logical cores. The server has 120 gig of RAM, and the server's cost amounted to around $10,000. For the NFS experiments, we use a NetApp FAS 6280. So before I demonstrate Chronicle's prowess in processing NFS workloads, here we compare the performance of underlying libtest library relative to other active model frameworks in Erlang and Go. To do that, we designed a micro benchmark where we create 1,000 processes that pass about 100 million messages in a ring topology, such that there are 100 outstanding messages at any given time. So here on the x-axis, we have different number of scheduled threads, and on the y-axis, we have the number of messages exchanged per second. As you can see, both versions of libtest outperform implementations in Erlang and Go by a wide margin. And we can see libtest scales well with the increasing number of cores. The only exception being for the NumoEver libtest, there is a drop from 16 threads to 32 schedulers. This is because when we introduce a second CPU, we introduce cross-socket communication, which resulted in drop in throughput. For an all-to-all benchmark, again, we saw similar results where libtest outperformed Go and Erlang by a wide margin. To measure Chronicle's maximum sustained throughput for different number of cores, we used a client that was issuing 64 KB reads and writes at an increasing rate until Chronicle's memory utilization started going up. The increase in memory utilization was a sign that Chronicle could not keep up with the workload. So for the rates that you see here, Chronicle actually maintained constant memory utilization, which means Chronicle can run at these rates for an arbitrarily long time, or at least as long as we have capacity to store traces. As you can see, Chronicle with 8 cores could sustain 14 gigabits per second, which was the maximum rate supported by the NFS server. Adding hyperthreading or adding the second CPU did not help much with getting better throughput because we were already supporting the maximum throughput supported by the filer with 1 CPU. What is impressive is that Chronicle, for all of these core configurations, used less than 2.5 gig of RAM. We also compared the number of NFS ops seen by the NFS server with the number of ops we captured in the trace to measure the loss rate. And for all of these core configurations, Chronicle achieved negligible loss. To measure the maximum sustained IOPS supported by Chronicle, we use the same methodology. But here we are using 1 byte reads and writes to exercise find under a high number of operations. As you can see, again, Chronicle with 8 cores can sustain 106,000 ops a second. Again, you can see here Chronicle used less than 100 meg of RAM to achieve this level of throughput. In one of our customer deployments, we actually saw Chronicle could sustain 150,000 ops a second for a metadata intensive workload that involved about 3,000 clients. So the previous measurements were done under perfect network conditions, where we used network taps, and there were relatively very few out-of-order packets or drop packets. To measure Chronicle's performance under a less than perfect scenario, such as when we are receiving reading packets through packet port mirroring, we did a control experiment where we modified packet readers to drop packets at specific 1-minute time intervals. So these intervals are highlighted on this graph, and they're annotated with the loss rate. For example, we're seeing 4% loss for this 1-minute interval. As you can see, when the loss rates are less than or equal to 3%, there is no noticeable effect on Chronicle's performance. However, for higher loss rate, we see that Chronicle gets slower in processing NFS operations. This is because RPC parser is operating in slow mode and is scanning packets byte by byte, and it stays in the slow mode well beyond the 1-minute loss intervals. But as soon as RPC parser parses all of the packets that are receiving that 1-minute interval, it reverts back to the fast mode and makes up for the lost ground. And this behavior is signified by these spikes after the dips. To validate that it was really RPC parser here that was the bottleneck, we can look at RPC parser's message queue backlog. So the conclusion we can draw here is that Chronicle can operate well under lossy conditions, provided that these losses are short-lived and we have a buffer of sufficient size to accommodate extra processing. So this is the last slide. Obviously, the trace storage efficiency in Chronicle very much depends on the workload. But here's an example of a 7-hour-long trace that we captured from a production environment. If we had stored this trace in PCAP format, we would have used 1.8 terabytes of storage. But performing inline parsing and checksumming of read and write data reduced that to 300 gigabytes of storage. Further use of data series inline compression reduced that to 44 gig. So in conclusion, Chronicle is a framework for capturing traces and analyzing workloads and light rate. It operates at 14 gigabits per second and is extensible to support other protocols and types of analysis. I'll be happy to announce that we have open source Chronicle under an academic non-commercial license, and I'll be happy to answer your questions. Thank you.
Hi, Tom Talpe, Microsoft. I have two questions, and they're slightly related. One is how much latency is injected by this processing to the NFS stream? And second, when you showed the rescheduling of tasks, you made me wonder, do you ever reorder operations in the NFS stream?
Okay. So as far as latency, because we are passively monitoring network traffic, we are not on the data path. So we're not adding anything to the latency.
Oh, but you said you were a middle box, so you terminate the connection and forward.
No, so this is a middle box that passively monitors network traffic. We are not on the data path at all. And the reason, for example, we saw the overhead because of packet losses and RPC parsers is because we are not on the end, one of the ends. That's why we have to scan packets.
If you're not an interposing middle box, that solves that question. Okay, thank you.
Xiaosong Ma from QCRI. Very interesting work, but I'm curious, this reminds me of the Shar's paper from Cal Physics. I wonder whether if you could have considered sampling and whether that will make a difference on the observations you give to your customers.
Okay, so I'm not familiar with that work. Maybe you can mention it again to me. But so for some application use cases, an IO by IO view of workload is preferred. For example, if you want to do caching analysis. But we've also implemented some kinds of analysis that are based on sampling. For example, for figuring out what are the top K clients or hottest files in a given workload, we are using some sampling methods that are pretty efficient. So for some application use cases, you may want to have an I/O by view of workload. For some application use cases, an approximate view of workload, for example, for figuring out the top K files or top K clients is sufficient. So it depends on the application use case, but both are possible through this framework.
Thank you.